Good afternoon, young people. It's Mrs. Rains. I am here to talk a little bit more about determining chemical behavior using the periodic table. We're going to delve a little deeper into the depths of the periodic table. Yeah, we're digging deep, guys. So first we're going to be talking about electrons, including valence electron configurations. Now, I know that several classes today were figuring it out. And so what is a valence electron configuration? The word valence means outermost or highest energy level. We already know that. We had this conversation about valence today in class. So the electron configuration for boron is 1s2, 2s2, 2p1. So the question then becomes, what is valence? What does that mean to be valence? So the highest energy level would be 2. So 2 would be the highest energy level. That's a good thing. So the VEC would be anything that has energy level 2. So that would be anything right here. So that would be 2s2, 2p1. That would be the valence electron configuration for boron, only the outermost, okay? So let's try another one. So electron configuration for bromine. Well, that electron configuration, notice I'm using the abbreviated version. I'm using argon, 4s2, 3d10, 4p5. So what's the highest energy level? Well, the highest energy level is the highest number that we see. The highest number that we see is the 4. The 4 is the highest energy level. So anything with the 4 would be valence. So the VEC would include 4s2 and 4p5. The 3D is not valence. So we write 4s2, 4p5. Okay? So that's pretty simple. So electron configuration for lead. Here we go. So what's the highest energy level? Okay. 6 would be the highest energy level. All right, the valence electron configuration would be 6s2, 6p2. Sorry, I don't know what it just did right there. Sometimes it does crazy stuff. Okay, so the 5 is not valence. Okay, we don't have to worry about that. We only worry about the 6. So magnesium, here we go. Neon, 3s2. What's its highest energy level? 3. Okay, what's its VEC? 3s2. So I've done several in different places. So you're going to practice these VECs. So go ahead and practice these VECs. Okay, hopefully you practiced some VECs and you got those taken care of. So valence electrons, what are valence electrons in Lewis dot diagrams? Well, we just talked about the valence electron configuration, yes? So we know that for like magnesium, the valence electron is 3s2. Well, what does that 2 mean right there? That 2 is the number of electrons. So how many valence electrons does magnesium has? It has 2. So we're going to be using that fact to figure out what's going on here. So let me erase that because that's not supposed to be right there right now. All right. So the number of valence electrons in a representative element is determined by counting the tall columns on the periodic table. So we don't have to know valence electron configuration. We can count tall columns. Once we know the valence number, then we use the symbol of the element. So X here represents the symbol of the element, and then we're going to use dots to represent the valence electrons. And since we're drawing an imaginary box around our little x, our element symbol, we can have up to 8 electrons. That means 8 is the maximum valence. So let's see. There's boron. Boron has 2s2, 2p1. That's a total of 3 valence electrons, and we see 3 dots. Nitrogen, we see 2s2, 2p3, that's 2 plus 3, that's 5. So we see a total of 5 dots. And notice how we put 1 dot on each side and then we come back in and put the second dot in. It's just the convention, don't panic. So now you're going to try these. Now you're going to try these, okay? All right, so on your paper, you should see something that looks very similar to this for your dot structures. So you can see that I've given you a view of what the dot structure should look like. Okay, so this is what you should have in your table. We didn't do these guys right here, so don't worry about those. But we did do, and we actually added period 7. So not exactly perfect, but it's there. So ions, what makes an ion? Well, an ion is made because an atom either wants to lose or gain electrons. And we already talked today about the fact that ionization energy describes what atoms want to lose, and electronegativity describes what atoms want to gain. So we know, in fact, that the things that are over here on this side of the periodic table want to lose, and that things over here on this side of the periodic table want to gain. So these are the losers, and these are the gainers. Okay? And we know that because of the trend that we have. So how can we get to a better idea of what's happening? So if we look at lithium, here is lithium right here. Lithium has one valence electron. If lithium were to lose that one valence electron, he becomes like helium, a noble gas. Okay? Or lithium would have to gain 1, 2, 3, 4, 5, 6, 7 electrons to become like neon. Well, that's a 7 electron gain, which is a pretty big gain versus a 1 electron loss. So if we talk in terms of money, lithium has to pay $100 to lose an electron or $700 to gain electrons to get where it needs to be. And just like the Chinese restaurant today, I'm going to want to pay the least amount to get the same cost. And if I can get to a noble gas of helium, I'm going to be okay. So lithium will lose an electron. So lithium has one valence electron. It will choose to lose that valence electron, having no valence electrons, having an outer valence looking like helium, and take on a 1+ charge. Now, how did that 1+ charge happen? Well, we know lithium has 3 protons, and lithium has, as an atom, 3 electrons. But if lithium loses an electron, it now has 2 electrons. So a +3 plus a -2 will give you a total of a +1 charge. So be really careful, because a lot of people say, well, I'm losing an electron, so that's minusing. So shouldn't it be a negative charge? But remember, you're minusing a minus charge particle. So minusing a minus is the same thing in math as saying plus. So be really careful with that. Beryllium. Let's look at beryllium. Well, beryllium, we know, has a dot structure of, sorry, my dots aren't drawn very well, has that dot structure. So beryllium's in a very similar position as lithium. What we have is beryllium choosing to either lose these 2 electrons to become like helium, or it's going to have to gain 1, 2, 3, 4, 5, 6 electrons to become like neon. Again, if we look at the energy cost, it's $200 to lose to become like helium and become a noble gas, or it's $600 to gain and become like neon, another noble gas. Either way, they're noble gases. So beryllium chooses to lose the 2, taking on a +2 charge. How does it do that? Well, there are 4 protons in beryllium. There are 4 electrons in beryllium. But if I lose 2 electrons, I'm going to have 2 electrons. And 4 plus a -2 gives me 2+. Remember, I'm minusing 2 minus charges. So that overall is a 2+. Okay? Boron. So we're just going in order. Boy, this is pretty cool, huh? So boron. Boron has an electron or a dot structure that looks like this. Okay, there's its dot structure. So boron has a choice again, just like everybody else. Remember, they're trying to become like a noble gas because noble gases are full. They don't desire to lose electrons. They don't desire to gain electrons. They have the highest ionization energies. They have no electronegativities. So they're in a perfect position to say, no, don't want anything. Thank you. No, thank you. So boron has a choice. It can either lose these 3 and become like helium, or it can gain 1, 2, 3, 4, 5 and become like neon. Well, again, if it's an energy cost it's having, 3 lost is better than 5 gained. So he's going to lose 3 and take on a +3 charge. Well, why does that happen? We have protons of 5, we have electrons of 5 starting out, but I lose 3 electrons, so I have a total of a -2 charge. 5 plus a -2 gives me a +3. Or we can look at it by saying minusing a -3. Those are equal statements, okay? So you're thinking, okay, here we go, carbon. Carbon. Here's carbon. Okay. Carbon has 4 valence electrons. Amazingly enough, it can lose those 4 and become like helium, or it can gain 1, 2, 3, 4. Hang on. It's an equal cost. Well, in reality, carbon very rarely forms an ion because of that cost. It doesn't choose to take that cost on. But officially, carbon can be a plus or minus 4. Why? Because carbon could go either way. The cost efficiency is either way is the same cost. It's $400. Carbon rarely chooses to form an ion. Now, anything that's a nonmetal or a metalloid that is more nonmetal-like will choose not to form an ion. But the metals will usually choose to form ions. So anything that's a metal will usually choose to form the positive ion. Okay? All right. So carbon's a little different, but we've got that plus or minus 4. Nitrogen, here we go, nitrogen. Nitrogen has 1, 2, oops. I'm not drawing very well right now. Okay, let's try that again. So nitrogen. Oh, it's acting funny. Nitrogen has 1, 2, 3, 4, 5 valence electrons. So it could lose those 5. It could lose 1, 2, 3, 4, 5 and become like helium, or it could gain 1, 2, 3 and become like neon. Well, again, we're at cost efficiency. Losing 5 is $500, gaining 3 is $300. So he's more likely to take 3 electrons from somewhere. And if he takes 3 electrons, remember nitrogen had 7 protons. He had 7 electrons, but he added 3. So now he has a total of 10 electrons at a negative charge. So that means he's got a total charge of a negative 3. Well, that makes sense. I'm adding a negative particle. I'm adding a negative 3. I'm adding 3 of the negative. So I get a negative 3 when I do that. So think about it differently. You can't think math, because if you think math, it'll mess you up in the head. Okay? That's nitrogen. Oxygen comes along. Oxygen has this dot structure. There's the dot structure of oxygen. Again, it can lose 1, 2, 3, 4, 5, 6 to become like helium, or it can gain 1, 2 to become like neon. This is a no-brainer. It's going to gain the 2, gaining 2 electrons, taking on a minus 2 charge. Oops, sorry. Taking on a minus 2 charge, okay? And that means oxygen, who had 8 protons, remember 8 protons, he had 8 electrons because he was neutral, but he gained 2. So now he has 10 electrons for a total of 10 minus. That means a 2 minus. Well, we added 2 minus charges, negative 2, okay? I think you're seeing here fluorine or fluorine. Here's fluorine. Fluorine can lose 1, 2, 3, 4, 5, 6, 7 to become like helium, or it can gain just 1 to become like neon. A no-brainer there, right? I'm going to gain 1. I'm going to gain 1, and I'm not going to be a plus. That's not right at all. There's no plus right there. Okay? I'm going to be a minus 1. Well, how did that happen? I've got protons of 9. I've got electrons of 9. I add 1 electron. That gives me 10 electrons. So I have a total of a negative 1 charge. Remember, I'm adding a negative 1. So those things are equal to one another. All right? So you should be able to figure that out. Neon. Neon, here we go. Neon. 1, 2, 3, 4, 5, 6, 7, 8 electrons. Guess what? Neon's full. Neon is not going to lose, it's not going to gain, it's not going to do anything. Neon is satisfied exactly where it is. So neon will do nothing. As a matter of fact, neon is a noble gas because it does not bond with anything else. All right, so neon doesn't form an ion, so it would just be neon. There is no ion. So now I want you to try these. Try these. So hopefully you've taken a moment and tried all of these. I will talk with you tomorrow. Thank you.